aircraft. 1 second. Yeah. So we're gonna be talking more about the airfoil shape and connection with aircraft stability today. And I think the stability part is probably going to overflow to Wednesday. And 1 second. So just actually. So we are not going to be discussing viscous flow until next week. So basically today we're going to be more talking about airfoil shape, and Wednesday we're going to connect it to aircraft stability, and starting to on Friday we're going to be talking about something related to viscous flows. That's a flow separation and stall on wings. So basically when the vortices are no longer on the boundary but goes to the free stream. Question? Yeah, exactly. For the quiz, the quiz is going to cover everything about the inviscid flow. So the flow separation is not going to be covered in quiz. All right. And there is no homework next week. Yes. Yes. So you are allowed to bring a cheat sheet to class, but no computers or cell phones use allowed. Yeah.
Bring a binder.
No, I remember I had something last semester. I'm gonna find out. So it's I think it's either one sheet or two sheet, two-sided or something like that. Yeah. So I'll find out and send it out as an announcement to you. Yeah. Yes.
How was performance on the quiz last year?
I don't remember, but I think last year, I don't remember the numbers, but last year the quiz, the first quiz was very good. Like I think I made the problem easy, so maybe a little bit harder this year, but not it shouldn't be too much. But like last year, I remember looking at the score was like the quiz one was like better than quiz two is better than like all the homework and project. So yeah. So last year was very good.
Multiple.
Can you get like practice problems? Like will they be uploaded?
So I may get some practice problems, but like the best problems for review is the problems we went over in class and also your homework problems. So I'll look over the materials and maybe there is one or two that's kind of extra in addition to the ones we covered in class and in homeworks, but like there shouldn't be too many. Yeah, so the type of problems that are going to appear in quiz is basically the same type that appears in class and in homeworks. And the homeworks usually involves more computation than you can do in a quiz, right? So expect covering the same concepts but less computation than the homeworks. Yes.
A typical structure of the quiz, like any questions. That I remember you showed one question that was like one with like 3, 4, 5.
I showed one question and I'll show the question again that has 3 parts. I think that was one of the 2 questions in the quiz, right? And you're gonna find out from today that the answer to these questions are actually pretty simple. I mean, yeah, if you are familiar with the concepts, you should be able to do this in less than half of the quiz time. Yeah. Okay. Any other questions? All right, and next week Monday there is no class, and Wednesday is the quizzing class, so regular class time. Quiz 50 minutes, starts at 11:05, ends at 11:55. All right, and on Friday, Professor Drayler is gonna come talk about boundary layer on airfoils. And in the afternoon, also Professor Drayler is gonna be talking about X-foil analysis of boundary layers on airfoils. All right. Okay. So today we are going to be discussing more about airfoil shapes. So we started on Monday in talking about the distribution of vortices on a cylinder. So this is assuming there is no flow separation. Basically, all the vortices are on solid body shapes. And starting from this Friday, you're going to learn more about flow separation. So if the flow, for example, separates over here, then there are vortices also over here, right? And that flow is going to be a combination of this flow. I mean, the realistic flow over a cylinder is going to be a combination of this flow, for which there is a vortex sheet on the solid body, plus what we started last week, that is the flow in a wave, which is a vortex sheet in the flow itself, right? So starting this Friday, we're going to be looking at more flows like that. Okay, and then we looked into thin airfoil theory. So thin airfoil theory basically solves a solution to this problem analytically, except for that the airfoil, the solid body in that case, has zero thickness, right? So a real airfoil is going to be a combination of a flow like this and the zero thickness solution. So the zero thickness solution essentially tells you the pressure difference between the upper surface and lower surface. So if you go to the thin airfoil theory example, we looked at two terms, and these two terms we went over last Friday already gave us a lot of information. So the first term is A0 term. So A0 term is basically a constant term in the slope of the airfoil. And if you integrate a constant in slope, you get a linear line, right? So that's basically the airfoil is having a constant angle of attack. So basically a flat plate at a constant angle of attack. And the vorticity distribution tells you the difference between the upper pressure and lower pressure. Okay, and what's the most important thing from this particular distribution is that this lift distribution, I should say, right? The pressure difference distribution, which we also think about as lift distribution, it's centered at the quarter chord. This is the whole reason why we usually measure the moments on the airplane around the quarter chord. And by the way, the pressure distribution or the pressure difference distribution is going to be a superposition, which means it's just a sum of the contribution from the different terms. If you add in the non-zero A1 term, the resulting pressure distribution is just a summation of a zero term, this one, with a non-zero A1 term but a zero A0 term. So you can actually look it up on the formula of G here, right? So I have A0 times the A0 term and plus A1 times the A1 term, etc. So it's just a linear superposition. Okay, so in the problem, for example, if you know what is A1, what is A0, right? You can actually add in the result of the A0 term and A1 term. So how do you do that? For example, if you know A0 term is equal to 1, then you know, for example, how much is the lift, right? And you know the lift is centered at the quarter chord, which means zero moment around the quarter chord. And then if you know also A1 term is non-zero, you know the A1 term is centered at the half chord, right? It is symmetric from the leading edge to the trailing edge, which means you know that you have another lift force that's centered at the half chord. So if you have both a non-zero A1 term and non-zero A0 term, the resulting lift and moment is just the summation of these two contributions. Okay, so that's the beauty of the thin airfoil theory. Okay. So CL is just a summation from the CL of these two terms. CM is also a summation of these two terms, except for CM is 0 for the A0 term, right? So it's just the CM of the A1 term. All right. So and this actually works for all the subsequent terms. And let me actually just go back to this particular example that I said was in last year's quiz, right? So the important thing to use here is that here we have two questions. that has to do with a change of angle of attack. And from thin airfoil theory, when you change the angle of attack, which term changes? Which coefficient, right? So I have the A0, A1, A2, etc. So if you change A2, look at the camber line. The camber line actually changes, right? And if you change A2, I'm going to talk about A2 later, but if you change A2, also the camber line changes. And what if I don't change the camber line, but only change the angle of attack? Which term change? A0, and only A0 change, right? Because if you change any other term, you actually change the shape of the airfoil. Okay, so now if you only change the A0 term, you're going to see what is going to be changing, right? So we said that the lift distribution is a summation of the lift from various terms. So if A0 change, we know how does the lift change if you change the angle of attack by a certain amount for a flat plate, which means if the lift coefficient is linear with respect to the A0 term, A1 term, etc., the changing the lift in response to the changing angle of attack actually doesn't depend on the shape of the airfoil, right? No matter what the shape of the airfoil, which means no matter what A1, A2, etc. are, the changing lift coefficient upon 1 degree changing the angle of attack is the same as if it is the airfoil is a flat plate, right? So we'll basically be using that for question 2. Okay, for question 3, you have to understand not just the changing CL, but also a changing CM, right? Because the question asks, okay, where is the center of lift? And if you remember, the center of lift, it depends both on CL and CM. If you came to the lab session on Friday, right, we asked you to, how do you manipulate the airfoil so that you get the center of lift at the leading edge? So the center of lift actually has to do with both. So you have to be able to predict, as you change the angle of attack, not only how does CL change, but also how does CM change. Again, because CM is a linear function of the A0, A1, A2, etc., when you change only A0, you only have to consider as if I'm changing my A0 for a flat plate, right? So the change of the lift and moment coefficient upon the changing A1 doesn't depend on what is the value of A2, etc., as long as this A1, A2 doesn't change. Okay, so which means for a flat plate, okay, for a flat plate, if I increase A0, how does the moment coefficient change? If I go up or down, how does the moment coefficient change? Look at CM. It does not change, right? Because the moment coefficient is measured around the quarter cord. And no matter what my A0 is, as long as it's a flat plate, the lift, no matter how big it is, positive or negative, is centered exactly at the quarter cord, which means CM is equal to 0. Okay, which means the change of CM as I change the angle of attack is equal to 0 for any airfoil. So that's going to be used to answer question 3. So I just laid out the principle. So please come to the blackboard and actually work out the answer to these 3 questions. All right.
So
Let me double check.
I don't know, what is it? Like, kind of like a triangle. It's like 5 times. What are each of those dimensions? Scale. What are each of these? Yeah, are these each 0.1? Or-
Yes.
Okay.
Yes, there are. Yeah. It's split into 10 sections.
Oh yeah.
Sorry, they didn't get an off.
Are we just doing like like on the quiz? You read along the way.
We can actually
You define like this is yeah.
Oh no. Actually, so problem 2, is it not just 0? If you assume 0 angle of attack and you basically thin airfoil that has like no angle of attack and it's symmetrical, and really making them with.
You're correct if it's symmetrical, but like if you look at the airfoil, does it look symmetrical?
Oh no.
Yeah.
So basically, you have pressure coefficient. So the pressure coefficient is
It would be nice.
zero. And the pressure coefficient is I wrote this down. Okay. My phone. Maybe you can plug like right way. I was just saying, just assume this is like a straight line until here, and this is also a straight market area from here. And also assume like this is a straight line. Yes. This other part.
Oh yeah, I should zoom out a little bit more. Yeah, the original angle of attack is so this actually shows 1 degree angle of attack. Yeah.
There's an equation. Right? And there's equation. So I got the equation in the home. It's like I don't remember exactly, but deriving that on quiz questions, like we can't even say CO.
It's like just
That's the result of like any result of the thing about theory.
Okay. Oh, the area? Like the area or this one? Well, the top one.
yeah, it's nice.
Yes.
area between
Set 180.
the four.
So oh, alpha speed radius.
Oh, they use S.
Yeah, I gave you like pi over 180.
Oh yeah, okay. So yeah, no, pi 180 is CL. 2 pi.
Oh.
Oh, it's zero. Oh no, but I did. Alpha is 1 3. Oh.
So, we know where and then
The alpha.
I guess
So the difference in CL is what we want to subtract 0.25 minus 0.1.
I already gave you pi over 180 equal to point, yeah, 1.7. Negative 0.1. So how did you get to minus? Right. Every thing, that's the plus. And then
Because you use this instead of that one. Well, yeah, because the DCL is tied to alpha. I feel like when you change alpha, it's 1 degree.
Oh, you're
So that's how you know like, when your change CL is going to decrease alpha by 1 degree. You just subtract that from your initial CL. Yeah, this is this. So we added this. So we know our CL because the graph is a CL at 1 degree. So if you know your CL at 1 degree, then your change in alpha would be like minus 1 degree. And so your change in CL would be negative. This would be minus that. And then combine those and get your new CL.
halfway there. It was like really weird. Yeah.
He's like, she's raising fish, I can't get out of it. Look around, yeah, you look where he was. It's like, ah, shit. Who's your quarterback?
Yeah. Pretty good.
Get recruited through the entire football. You don't have one?
I don't think he's able to, or actually,
it's 0.9, not 9.
Oh my, for real.
It's okay.
Got it. I know what mine is. Yeah,
I screwed up everything. I always think like use it early.
yeah,
Once it's add up. Usually it doesn't.
I just always think I'll mess up like I always just hear positive and then at the end I do like the right hand.
Yeah, exactly.
This is correct. I'll be like that way.
Fair enough.
Triangle, like a little triangle on the side. Fuck that.
Some of the
Don't even worry, bro.
yeah, it's nice to meet.
Same order of magnitude.
This is like that. It's like oh, that one. This is Scalper.
Pretty good.
You got through 1.5.
Oh, no, we're burning it from oh, wait. That 1 degree angle of attack in order to show this. What is the center lift at? This is 1, right?
That is the way. Like MIT or
Then we can yeah. I don't know how that works. What?
I heard it like might not be able to because there's that's supposed to be like
Center of
like if anything was at that point, like I would just like I would just ran to the bathroom. Yeah, stay with them. Unless like they're skinny. All right, man. Like usually
regardless of time.
The history of the location.
Yeah.
Yeah, that's what I heard. Oh yeah, like and then this side also like CL at 1 degree minus CL at 0 and mine subtract and
Okay, so this is from you, right? This is so the box is gonna have an area of 0.6. Oh, yeah. You need to multiply this by 0.1. Yeah. Okay, so then it makes a lot more sense.
assume that CM is constant. It's like this really small angle. Okay, then fine.
Wait, so CM is constant according to linear theory,
Okay.
right? So as a tangent of attack, it doesn't change CM.
Okay.
That's that's the key for problem.
Yes, then I think we got that. Yeah, fine.
Can I pass
Oh,
over?
yes.
Okay, thanks.
For free. I don't know if it's all the quarter chord though.
Okay, so first of all, for question 2, the set of list is not at the protocol, right? Because the list, the set of list is at the protocol only if and only if the CM is equal to 0.
Oh, so we just do CL over CL, is that what we have to do CL?
Yes. You have a UCL, but this is always given as 0 degrees. This is 2 for 1 degree.
Okay.
So as it reaches the angle of attack, like what does it mean? How do you figure out how does CM work?
Might know like how much CL. Or how did you like where the center is? Sure.
Also, remember like at the angle of attack, this is only the A we learned. Sorry, only the A0 we learned. So the A0 term corresponds to a lift at the protocol. Right. It doesn't contribute, the A0 term does not contribute anything to CM.
Okay.
Which means as the angle of attack changes, CM doesn't change. So you use this to figure out what is CM at 1 degree.
I was just going to do the simple.
You know, it's going to be the same at 0 degrees.
Oh, okay.
And plus you know the lift at 0 degrees, right? So
Yeah,
you
but I
use
wasn't sure
that.
if it's conventionally.
I would have written it. That's not sure.
Yeah.
Okay. I think.
Oh yeah, I just had that sort of, but then I took it out. It's just two directions. Let me know what that about is.
Well, this is the same. Actually, plug in. But I wasn't sure what it is.
I don't think it's yeah, at 1 degree, I gave you the ratio, right? I see. Point 7.
But I answered it this way.
Okay. Oh, okay. I'm just in the last one.
Actually, no, do that. I can says that's the function. Okay. When you do the quiz or something, type arithmetic to your math, otherwise it's kind of wasting a bit more time. Yeah, it's fine. We get the right answer.
Yeah, okay. Good. I think I saw everybody got the right answer. So, any questions? I don't think it's worth going through the answer again, right? So basically, I think all of you got it. It's you estimate the lift. I see many people use different shapes to approximate the area. Like they all work, right? Just a different amount of work, but like you all roughly get the right thing somewhere between like around the 0.2 point. It's all pretty good, and at 0 degree angle of attack, you subtract that 0.2-ish number you get at 1 degree angle of attack by 2 pi times 0.017, right? This is the how much the angle of attack has decreased, and you know the change in the lift as you change the angle of attack is 2 pi times the changing angle of attack. You also know that as you change the angle of attack, the moment doesn't change, right? You're only modifying the A0 term, which contributes nothing to the moment coefficient around quarter chord. So you use this ratio to calculate the CM at 1 degree angle of attack by multiplying this minus 0.07 by the CL at 1 degrees. And then you carry the same CM for 0 degrees, right? And then you figure out what is my old CM, which is also the new CM, divided by the new CL you calculate from question 2. And that way you're going to get the ratio for 0 degrees, which is really just the distance from the quarter chord to the center of the lift. All right, and in this case, the number is negative, which means the lift is downstream of the quarter chord. Okay, any questions? All right, okay. So today, let's actually spend the remaining of the time talking about the A1 term. So that's the last term that I think is useful to understand, right? So all the remaining terms you just need to know is there, right? If you have a precise shape, they just corresponds to fit in the precise shape and changes the pressure distribution somehow. But the A2 term is the last one I think is useful to understand conceptually. So if you look at if I change only the A2 term, the A2 term is a cosine of 2 times t, which is t is actually arc cosine of x. So this basically gives you a quadratic as a function of x in the slope, which you integrate to get a cubic in the camber line. So if you look at this red line, it's a cubic, somewhat. And what's specific about this cubic is that when you actually see an airfoil, it reflects itself in what we call a reflex shape. So have a positive camber on the leading edge portion, but a negative camber at the trailing edge portion. Okay, so whenever you see something that goes like a fish, goes upward around the trailing edge, you know this has a significant A2 term. All right, and then what is the effect of the A2 term? The effect of the A2 term is going to also have a pressure difference distribution that's positive around the leading edge but negative on the trailing edge. So what does that mean? That means I'm creating lift force, positive lift force around the leading edge, but negative lift force around the trailing edge. Right? Does that remind you of kind of the horizontal tail we have been looking at both in class and in homework? Right? So basically, you are lifting in the front portion of the airfoil and pushing down on the back portion of the airfoil. So this is the most effective way of shifting the center of lift towards the leading edge, right? So if I put this airfoil at a positive angle of attack, you're gonna get a lift distribution like that. Usually, there is also a non-zero A1 term. So essentially, you're gonna get a pressure distribution that looks like this. There is a lot of lift in the front portion. On the back portion, there is either almost a zero lift or even creating something negative, right? For example, if you look at the center of lift here, it's like 4% from the leading edge in this case. So this is, and in contrary to what you did the last Friday of creating an airfoil that looks like this, right? This airfoil, as we go to the viscous part, still has good stall properties. If you look at the airfoil you build on Friday, right? You put the airfoil at a negative camber, or you put a positive camber airfoil at negative angle of attack. The flow would separate from the leading edge actually pretty early, so it won't have very good CL max. This airfoil can have lift concentrated more towards the leading edge, but still have pretty good CL max. Okay, so one of the questions that you may find possibly in the quiz is something like this. I think this is also another quiz question. I don't remember which year, not last year, but like there was a question in looking at these two airfoils, and there are two pressure distributions. The question is, can you match the airfoil with pressure distribution? Okay, I think that quiz may even have more than two airfoils and more than two pressure distributions. So you end up having to match the airfoils with the pressure distributions. The question is which one matches to which. Yes? That's correct. What is the rationale?
I got a question for this. I was it's like for top one, positive character, and what positive character, or and then have
Very good, very good. So this airfoil is an airfoil that has what we just mentioned, the reflex shape. Okay, so if you trace the camber, so the camber is the midline between the upper and lower surface, right? So you have a positive curvature all the way to here, but around the trailing edge, you are starting to get a slight curvature in the opposite direction, right? That's really constructed by, it doesn't have a A2 term as much as this, right? But like something more like this. It's something more like this, right? So this would it may have a bigger A1 term and something like this. So this is closer to the camber that we saw in this airfoil, right? That has a pretty significant both A1 and A2 term. Now you put it at a positive angle of attack, something like this, you would see a pressure distribution. Well, if you look at the difference between upper and lower surfaces, you would see like a pretty big region in front, but at the back it very quickly shrinks to something that's almost nothing, right? And also, a question is, why don't we see this huge spike in the leading edge? Why don't we see this huge spike in this case, negative pressure, right? In this distribution. Well, the answer is because this airfoil is thick, right? It's not a thin airfoil. So as we said, the thin airfoil theory is never correct at exactly the leading edge. And the thicker the airfoil is, actually, it's more about the radius of curvature on the leading edge. The fatter the leading edge of the airfoil is, the more wrong thin airfoil theory is around the leading edge. So in this case, yeah, this airfoil has a very thin leading edge, but this airfoil has a very blunt leading edge. So you wouldn't see the pressure spike actually in this airfoil. For this airfoil, although has a very thin leading edge, but you can see this pressure distribution corresponds to a very significant A1 term, right? So if you get rid of my A2 and only has an A1 but have 0 A0, you would see a pressure distribution that's more like what we see over here, right? And actually be more accurate if I also make some A3 terms. So this would be actually even better approximation to what we see over here, and get something like this. So all of this actually changes the pressure distribution somewhat, and this is this makes it even more flat topped. So this is very close to the distribution 3 you see, right? Okay, does it make sense of how we are kind of connecting the pressure distribution to the shape of an airfoil? Yes?
Is there ever a case where it's misleading? Like that.
Is there ever a case where it's misleading? I would say, like, for very thick airfoils, the thin airfoil theory related analysis is no longer very useful. It can be quite misleading sometimes. But for thin airfoil, I mean, when the airfoils has like a thickness to chord ratio of like around 10% or less, it's actually pretty useful, pretty good. As long as you don't stare at the leading edge, it's it's good. All right. Okay. If there is no other questions, let's end the class now, and we'll come back on Wednesday and talk more about how does the shape of the airfoil impact stability of airplanes. All right. Yeah.